Hello everyone, welcome back. I'm here to show you today how to make a metalens component in the PlanOpsim software using structures that we've simulated earlier. And now going to place those individual nanostructures all together on a substrate to make a lens out of it, and then also generate the GDS mask in order to then send this off for lithography. So let's start at the beginning at selecting the individual nanostructures that we will be using. I've made a previous simulation here where I have a number of nanopillars made out of titanium dioxide surrounded by air on a silicon dioxide substrate. I'm happy with that design, and now I want to go ahead and place those structures in a component. The first thing I want to do when making a component is to select the nanostructures I want to use for that component, and we'll call that a family. And inside a family, there are a number of family members. That's the individual nanostructures that we will be able to use them in the end. Now, to make a family out of our individual nanostructures that we had here in the sweep calculation, I need to go to the Library tab, where you'll notice that here on the left-hand side, there's a panel called Structure Families. We'll click there. This will bring me to a table of all the structure families that I've got. So in this case, I want to make a new one, so I go and click the Add button and give this family a name, for instance, of all this TiO2. I can enter a description, so these are pillars for metalens, and I need to select a unit. I usually like to work in micrometer, but then also micrometer, and then save that. And voila, we have here a new family of nanostructures. Now this is just an empty family at the moment. When I expand this here, see that there's under the list of members, there's nothing in there. So I need to add these members now from my previous simulation. Add button. This will open up a little wizard, which has 3 steps. You see on the left, 1, 2, 3. And in the first one, there's a table of all simulations that I've done. You can scroll through all of them. I will just select the latest one here called Simple Metalens. That will tell the software that I will be looking for structures inside this calculation. I can combine structures from calculations as long as they are compatible. I'll go to next. And now it will ask me to choose specific results from the selected simulation. So what it will show then is what I'm seeing here is the plots that I've made for the simulation. So I've plotted here the transmission to see that, for instance, here at this height of 650 nanometer, I have a series of structures that are having high transmission. And I've also plotted the phase response at that same 650 fixed height. Now, if I'm missing a plot because I just forgot to plot something, you can just add it here by clicking Add Plot. I don't need this now. Now, how do I select individual members from the simulation? Well, all I have to do is hover over the plot. Best to do this with tooltip enabled so that you will see exactly which value you're pointing at. And then I will select a number of nanostructures for my calculation. So let's start, for instance, here on the left with a component that gives a structure that gives minus 30 degrees phase. So I'll select this one. If I now scroll up, I'll see that in the list of selected values, I have here this one simulation. I'll like to add a few more. Let's keep it simple and just select 4 members, but of course you can select as many as you want. So let's take 3 more. We had a phase of minus 30 degrees already, so let's try and cover the whole 0 to 360 degrees phase and select one at minus 120. So, for example, this one here is giving minus 122 phase. So good. Then I also want one at plus 60 and plus 150. So 160, and yeah, let's take 141, close enough. And I'll go here, I'll see my 4 individual structures. I'm happy with those, and I'll go on to the next step. I'll click next. And this will just show me a summary of the family members that I've selected. They're given a name 0, 1, 2, 3, which I can change if I like. So I'll call this pillar 1, for example, and also rename the others. Voila, these are all 4. Save that and click finish. And with that, it will add these structures to my family that I can use in a later designs of MetaComponents. Now that I have selected the family members, I once again can have a look at the structure families table where we see the TiO2 family that I just created. I can expand it now. It used to be empty, and now we'll find that all 4 of our structures are listed in here, as well as a small summary of what's the difference between each individual structure. And with that, we can go on to use that family in order to create MetaComponents. So to do that, we've got a family. So now we need to go here into MetaComponent and create a new component. This has a project tree similar to the meta cell. So we have projects, which you can think of as folders, and within this projects there are individual components. So let's make a new folder called TiO2 components, and then let's make first simple lens in there. Voila, this will get me a new component with this window here, where I have to select on the one hand what the dimensions of the component will be, so how big it will be, and which family members I will use. I'll go to component dimensions and set a component, for instance, 250 by 250 microns, small metalens. Save that. And I also need to choose which family, which structures I want to use to make this. So I can edit that family, pick my TiO2 family that I had before, and then you will see a list of all the members that were in this family. I can choose any number of members that I want to use inside the MetaComponent, or I can just use all of them, move them over here, save that, and then we'll list these members. The MetaComponent itself will only use the selected members of the family. So if I have a family with lots of nanostructures inside, but I only select 4, it will still only use those 4. I can give a description as well. So I'll just description to based metal. Voila. And then we can move on to the next step, which is defining the near field wavefront target that we want to create, the near field wavefront that we want to recreate with our metalens. Now that we've created the MetaComponent, the next step is to set the target for the component. So that is, by that I mean we need to select what the desired wavefront exiting the metalens should be for a given incident angle, wavelength, and so on. So in order to do that, we go one view below here into the target settings, and we'll see there that it's now empty, and there's just a table called Design Targets where we can add new targets. So let's add one target here and edit that. On here, select it. We can click now this target, which is filled with default values for now, but we can go about setting that up. So you'll notice there's three tabs that have three groups that have popped up here. One is the design target details. This will be used to set what the incident light will be like and which quantity I'm interested exiting the lens. On the other hand, we have here below target far field and near field wavefront. This allows you to choose either one, either a far field or a near field wavefront that the lens should reproduce given the certain input settings from the set point. Let's start by defining the exit configuration and the incident light in the set point. So I'll add it here into the details. I will give this target a name first. So let's call this a lens for 600 nanometer. Description. We are interested in getting a certain behavior for the 0,0 diffraction order, and we would like to get that in transmission or reflection. In this case, I'll pick transmission. We are interested in the TE polarization in this case, but we select other polarizations as well. And we most of all want to reproduce the complex phase and amplitude of the wavefront that we will be setting. Like this. So what I've now told it is that this metalens should work in transmission for TE polarization, and it should reproduce the phase and amplitude of the wavefront target that we will set afterwards. What we still need to say is what light will be incident on the component. That's done in the set point that we can select here. We have multiple set points, but let's create a new one. The set point on the one hand is the incident light settings. On the other hand, it's a setting for the solver to calculate. So if we solve with a certain accuracy setting, it will take that one for all calculations of nanostructure behavior that we will need to approximate the wavefront. Let's start with taking our accuracy settings. Set this to 3 by 3, which is the same as I had for my family member when I simulated it originally. It doesn't have to be the same. So if I want to put something else, let's say I want a more accurate simulation now that I'm actually going to make the MetaComponent, I could set this to 5 by 5, for instance, and that will just trigger a new simulation whenever it's. For incidence, I'm going to start by a simple case, just saying that there's normal incidence with a unit amplitude for the wavelength of 600 nanometer. So I can use that nanometer here and save that set point. Voila. So now we've selected 600 nanometers as the wavelength that we are interested in. And we go down a bit and define the near field wavefront. As a first example, I want to take a very well-known wavefront that you find a lot in literature. It's the theoretical equation for an aspheric lens. This is a profile that stipulates that in the focal point, the entire wavefront, all rays arriving there, should be in phase with each other in order to create, in theory, a perfect focus for that wavelength. So I go to the near field wavefront target and I hit that. I need to set the dimensions of the wavefront I want to use. These should be at least as large as the size of the component, because, well, they should be no larger than the component. The component cannot create a wavefront that's bigger than the component itself. So by default, it's set to the same size as the component. I'm happy with that. And then I also need to import the wavefront's amplitude and phase into my calculation. So I've prepared a little file for that I can now upload as a JSON file. So I can drag and drop this here. I'll go and take my wavefront that I've prepared, drag that into the box and let it upload. And you should see it pop up then in order to show the amplitude and phase that we've selected. Here it is. So I've implemented this equation, so it has a unit amplitude, and for the phase we will have a spherical symmetric pattern that focuses at a fixed distance. Here I've selected 500 micrometer away from the, so I'm making a lens there. There's the phase. You'll notice this is in radians. It's going from 0 to a little bit over 6, 2 pi to be exact. This is the wavefront that we will try to approximate. This is the ideal analytical wavefront that we have. We're happy with amplitude, we're happy with phase. Save that. And like this, we have defined our design target, and we're ready to go on and let the solver do the hard work of approximating the wavefront using the nanostructures. To do that, we go to Design, and similar to a meta cell calculation, we just have one button here, which will allow us to start the design job. Click Start Design. Now that I've defined my target, all I have left to do is let the solver do the hard work of placing individual nanostructures wherever discretized over the whole MetaComponent to reproduce the near field wavefront. So to do that, I go to Design and click the Start Design button. And now the solver will loop over each of the structures and create an approximate. And now, once that's done, I'll be able to inspect my component and take a look at the GDS mask. So I can generate a report with some details about this calculation here as a PDF, which will then download. And I can also generate the GDS mask here by clicking Mask. And this will then download the mask as well. And if for some reason I've changed something and I want to restart the design, I can do it too. So let's take a look at the GDS design to see that we have actually created a. I've opened the GDS file in KLayout, and what you see here on the left is we have something called Metalens, which inside the first layer has 4 sublayers which have the names of my components, of my nanostructures, so pillar 1, 2, 3, and 4. And I also have an area of 250 by 250 microns that will be the GDS file. If I zoom in a bit here around the center, you see the same spherical structure, circular structure appear as I had in my near field wavefront. That's because we are approximating this near field wavefront using the 4-pillar structure. So like that, we have generated out of a series of nanostructures metalens focus with a specific wavefront that we defined inside the PlanOpsim software.